Hello class, today we are starting Chapter 8, which focuses on factoring and quadratic equations. Today's lesson will be Section 8.1, which is monomials and factoring. By the end of today's lesson, you will be able to factor monomials completely and find the greatest common factor between a pair or possibly three monomials. When we're talking about factored form, this is when a monomial is written as a product of prime factors. Remember that prime factors are numbers that can only be divided by 1 and itself. So all of the numbers in our final answer must be prime numbers, and all of the variables have an exponent of 1. So for example, we had a to the second power, we would have to write out a times a, because we need to make sure that those exponents are 1. Reminder again that product means multiplication. So we're going to be multiplying prime numbers and prime variables. Additionally, later in the lesson, we will be talking about greatest common factor. This is the largest monomial that can divide the original monomials. So just like greatest common factors with numbers, we're looking for the biggest number that can divide 2 or more terms. And this time it is going to include variables since we are talking about monomials. Greatest common factor is going to be a huge piece through this entire chapter, so it is very important for us to understand this concept starting now. Factored form. So we have factor negative 52a to the fourth b completely. So we deal with the numbers first. If you have a negative number, your first job is to pull the negative to the outside. So negative 1 is that first prime factor that we're going to pull out if we have a negative. So negative 1 times 52 gives us negative 52. Now I need to break 52 down by prime factors. I can divide by 2. 52 divided by 2 gives me 26. Again, I can break that down into 2 times 13. Both 2 and 13 are prime numbers, so my factor tree is complete. In order to write the answer in final factored form, we're going to have the product of all of our numbers. So negative 1 times 2 times 2 times 13. Remember, all of our prime numbers are at the end of one of the branches. And then when we are writing out the letters in factored form, or those variables, I have a times a times a times a to represent a to the fourth times b for b to the first. So our factored form is negative 1 times 2 times 2 times 13 times a times a times a times a times b. Notice that the numbers go from least to greatest, so those numbers when you write out the prime factorization should go from smallest to largest. Go ahead and try this one on your own. Factoring we can break down into 6 and 8. You could have started with 2 and 24. You could have started with 3 and 16 or 4 and 12. However you chose to start, you factor down to 2 times 2 times 2 times 2 times 3 times n times n times n times p times p. So breaking down each part as completely as we can get. So now we are working on finding the greatest common factor, or the GCF. We can do this by a couple of different methods. The first option is to use that factor tree. So we just used the factor tree for 48 and found out that our final factors were 2 times 2 times 2 times 2 times 3. We could do the same thing with 64, breaking it down into 8 and 8. Both of those break down to 2 and 4. And both of our 4s can break down to 2 and 2. So giving us 6 2's being multiplied for the prime factorization. To find the greatest common factor, we are looking for what these two have in common. So I've got 1, 2, 3, 4 2's over here, which means I can match 4 2's on the other side. 2 times 2 is 4, times 2 is 8, times 2 is 16. So the biggest number that can divide 48 and 64 is 16. Then I'm going to go ahead and pay attention to my variables. So on this first one, I would have 4 G's and an H. And on the second one, I've got 3 G's and 2 h's. Looking at what they have in common, I've got 3 g's on the second one, which I can match on the first one. So 3 g's. And then I have 1 h from the first one, and I can match an h from the second one. So I can pull out an h from each of them. So our greatest common factor here is 16 g to the third h. The other option I have for how to find the numerical portion of this is by using multiplication factors. So I can list out 1 and 48, 2 and 24, 3 and 16, 4 and 12, 5 doesn't work, 6 and 8. So those are all the multiplication factors of 48. I can do the same thing with 64 and list 1 and 64, 2 and 32, 3 doesn't work, 4 and 16, 5 doesn't work, 6 doesn't work, 7 doesn't work, 8 and 8. So now if I'm looking at these two lists of purple numbers, I'm looking for the biggest number that they both have in common. So they both have 1, not the biggest, 2, but not the biggest, 4, not the biggest, 8, but not the biggest. 16 is the biggest number that can be found on both of those lists. Again, then we look at our variables. We had 4 g's over here and 3 g's over here, 1 h and 2 h's. Again, we're looking for what they have in common. We can at most have 3 g's because there's 3 g's in the second one. There's 4 in the first, but in common they have 3. 2 h's in the second, 1 in the first, so in common they have 1. So either way you want to figure out that answer, our final answer for the greatest common factor is 16g to the third h. Go ahead and try this one on your own. So again, you can see the factor tree method up top or the multiplication factors down here on the bottom. Either way, the greatest common factor for the numbers is 6. We can pull out an a that they have in common and a b squared that they have in common. Similar kind of setup here, we're just looking at a word problem. So our two numbers, we've got a florist that has 20 roses and 30 tulips to make bouquets. What is the greatest number of identical bouquets that she can make without having any flowers left over? And how many of each kind of flower are in each bouquet? So what this is asking us to do is figure out that greatest common factor, and that's going to tell us how many bouquets we can make. So I've got 20 and I've got 30. Breaking down 20, I can go 2 and 10 and 2 and 5, giving us a factorization of 2 times 2 times 5. 30 can break down into 2 times 15, which breaks down into 3 times 5. So 2 times 3 times 5, which means what they have in common is a 2 and a 5. So that gives us a common factor of 10. So that means we can make 10 identical bouquets. And then when it comes to how many flowers of each type, that is looking at our leftover term here. So in those 10 bouquets, we can have 2 roses and we can have 3 tulips. So we can take that many out of each grouping to make 10 identical bouquets. Again, if you wanted to do this using the multiplication factors, you could have listed out 1 and 20, 2 and 10, 4 and 5 for 20, and for 30 it would be 1 and 30, 2 and 15, 3 and 10, and 5 and 6. Again, 10 is our common number for both of those, the biggest number that they have in common. Go ahead and try this one on your own. We've got the factors of 84 and the factors of 70. When I break those down, our greatest common factor is going to be 14 for both of them. If you have questions about this or any other part of the lesson, please let me know when you get to class.